Hey everybody. So one of our topics for this week is ellipses. And I found a video that does a pretty nice job of explaining what they are, and I'm going to stop it and narrate some things along the way. So let's check that out.
Hey everyone, welcome back to Rapid Math. In today's video, we'll be answering the question, what is an ellipse? This is a viewer requested video. Always appreciate those requests. Be sure to leave yours down in the comments. With that said, let's start talking about this very cool shape, the ellipse. In this video, I just want to give you a good idea of what an ellipse is and introduce some related terms. There is a number of different ways that we could define an ellipse, but in this video we'll be focusing on the definition that I think is most common, most intuitive, and to me most interesting. Alright, that's enough dilly-dallying. Here is a beautiful example of an ellipse. An ellipse is defined by three things. The first two things are these 2 points. Each one of these points is called a focus of the ellipse. So together, they are the foci of the ellipse. That's the plural of focus. So again, an ellipse is defined by 3 things. The first 2 are the foci. We'll call this focus F1, and we'll call this focus F2. So what's the third thing we need to define an ellipse? The third thing that you need is a distance. Let's say that we pick a distance of 2a, and you'll see why we chose to write the distance as 2a instead of just a in a couple of minutes. But this is the third thing we need to define an ellipse, the distance. This 2a is just some number. Then what's important about this distance? What does it have to do with our ellipse? Well, let's say that we pick a random point on our ellipse. Let's say a point right there. Then we could consider the line segments from this point to the foci of the ellipse, these 2 line segments here. And let's just call this point P1. Alright, this is the part where we learn what's special about this distance. Let's say that we add the lengths of these 2 line segments, and we can write that like this. The magnitude of the line segment.
So he uses that term magnitude right there. You don't need to know that term. He's really just talking about the length of the segment that connects P1 to F1. So you don't need to worry about that notation that he's using right here.
From P1 to F1, written like that. So that's the length of the segment P1, F1. And then to that, we're adding the length of the line segment from P1 to F2. So what do we get if we add the lengths of those 2 line segments? What we get is this distance that we chose, 2a. So given 2 foci and a distance, an ellipse is the set of all points such that for each point, the sum of its distances from each foci is equal to that original given distance. It's kind of similar to what a circle is. You might remember that a circle is a set of all points that have the same distance from a center. In an ellipse, the distance from any point to either of the 2 foci is not always the same, but if you add up those 2 distances from each foci, that sum will always be the same. So if this green point that I just drew is P2, then we could write that the length of the line segment P2F1 plus the length of the line segment P2F2 is, of course, equal to 2a. So pick any point you want on an ellipse. If you add up the distances from that point to the 2 foci of the ellipse, you'll always get the same number. And this isn't just similar to what a circle is, it's actually a generalization of circles. So a circle is actually a special kind of ellipse. A circle is an ellipse whose 2 foci are the exact same point. You can imagine that if we were to sort of squeeze this ellipse in at the sides until it resembled a circle, these foci would get closer and closer and then finally come together to make that one center of the circle. So a quick recap so far. What we need to define an ellipse is 2 points called the foci of the ellipse and a distance. Then the ellipse that information gives us is the set of all points, so that for each point the sum of its distances from the 2 foci is equal to that original given distance. And a circle is a special type of ellipse. It's an ellipse whose foci are the same exact point. Alright, so that's the most important stuff out of the way. The most important thing about this lesson is that I want you to come away understanding what an ellipse is. But now let's talk a little bit about some important related terminology. Consider the line segment that passes through the foci of the ellipse and whose endpoints are both on the ellipse. This very special line segment is called the major axis of the ellipse. Something very cool about the major axis, guess what its length is? Its length, sure enough, is 2a, the original distance that we used to define the ellipse. And we can talk more about exactly why that's true another time, but it's certainly a beautiful property to keep in mind. Alright, now let's focus on the two foci of the ellipse again, pun completely intended. Consider the midpoint of the line segment connecting the two foci. That midpoint is about right there. So this point is equidistant from F1 and F2. But what's so cool about this point that we just drew? Well, this neat little point is called the center of the ellipse. And the center is also the midpoint of the major axis. So since these two distances are equal, and together they add up to 2a, we know that this distance is a, and this distance is a. Alright, that's neat, but another thing we can consider is the line segment, whose endpoints lie on the ellipse, is perpendicular to the major axis and passes through the center. That's going to be approximately this line segment right here. This line segment is perpendicular to the major axis, its endpoints lie on the ellipse, and it passes through the center. And this brown line segment is called the minor axis. The major axis of an ellipse is always greater than or equal to the minor axis in length. Of course, when the two are equal, what we're looking at is a circle. But if it's not a circle, then the major axis will be greater in length than the minor axis. Alright, there's really just two more quick things we've got to talk about. I'm going to clean up some of this stuff on the side so that we have a little bit more room to work with. Shrink this down, put it over there. If we just consider half of the major axis, we have a special name for this.
So these are also names that you don't need to know. So when he talks about the semi-minor axis and the semi-major axis, those are not terms that you need to know. But the major axis and minor axis are terms that you need to know. But the semi-major and semi-minor you do not.
Called the semi-major axis. And remember that the semi-major axis, which is half of the major axis, has a length of a. That's half of the distance that we use to define the ellipse. And you might not be surprised to learn that we also have a special name for half of the minor axis. So if we consider this green segment here, this is called the semi-minor axis. The length of the semi-minor axis is usually represented by the variable b. These two measures, a, the length of the semi-major axis, and b, the length of the semi-minor axis, are used in a lot of calculations regarding ellipses, so that's why they are important. And so now you can see, by originally describing our distance as 2a, if we were to go on to write the equation of this ellipse or calculate its perimeter, just for a couple of examples, we would get to use this nice variable a. Whereas if we had just defined the distance as d, then this would be 1/2 d, which doesn't look quite as nice. So just a quick recap of the second half of things we talked about. The center of an ellipse is the point that's halfway between the two foci. It's also the midpoint of the major axis, and I don't think I said this earlier, but it's also the midpoint of the minor axis. The major axis is the line segment that passes through the two foci and whose endpoints are both on the ellipse. The major axis has a length of 2a. Half of the major axis is called the semi-major axis and has a length of a. The line segment that is perpendicular to the major axis that passes through the center of the ellipse and whose endpoints lie on the ellipse is called the minor axis of the ellipse. Half of the minor axis is called the semi-minor axis, whose length is usually denoted by the variable b. Those two lengths, a and b, are used in a lot of calculations regarding ellipses. And one last thing before we go.
So just so you know, in this picture, the major axis will actually run vertical. So as he's mentioned earlier, the major axis is always the longer one. So it doesn't actually, the major axis doesn't have to be horizontal. It might be vertical if the ellipse looks like this.
Just wanted to show you an example of a tall and skinny ellipse, and here are its two foci. Alright, so that's just a whole bunch of stuff about ellipses.
So here's if you start Googling and looking for videos of ellipses, a lot of the things you'll find up that will come up will be carpentry videos. So here's one. I'm going to start you most of the way through it. He's run through some constructions and he's placed some nails in the table. And he's doing this, he's going to create a tabletop that's an ellipse.
With a pencil, pull the string taut and just kind of let the string guide the pencil as you form an oval stroke around the table. Now with this one, you'll notice there's a few spots where the pencil snags. That's because this top isn't perfectly flat yet. I'm going to run it through the drum sander later to take care of that. Now you should only need to go around once. I went several times to really darken it up so that it would show up well on camera.
So here's another one that I found. He's actually doing an archway, so he's actually going to just do half of an ellipse.
So now that we all understand what the major axis is and the minor axis of our ellipse, what we're going to do is actually lay one out using what we call the string method. This is the most simplest way to do it, the easiest way to lay out an ellipse. It's good for framing, it's good for layout, show the customer exactly what they're going to do. So let's take a look at this. We're going to start first off by setting our major axis, or the baseline, for our elliptical shape. And I'm going to do this just using a board to keep myself nice and straight. Clip this up. So we're going to draw the baseline for our ellipse. Nice line here. Board is 48.5 inches wide. So a 24.25. Make our center line. Framing square. This needs to be 90 degrees perpendicular. Set that right over the line and up to about 14 inches here.
So in this one, he actually knows the width of the doorway and he knows how high the arch is. So he's actually going to now have to find the foci.
Now the width is going to be 40. So we have our 20-inch mark and we have our 40-inch mark here. We're going to draw this using what we call the string method. First thing we need is a string, or in this case I'm using a piece of picture cable. It doesn't stretch, and that's the neat thing about it. If you were to use cord or string, there's a little bit of flexibility in that, so when you go to draw it, your shape might distort a little bit. First thing is we want to define the outside of our elliptical shape. So I'm going to get a couple of screws here and we'll set this up. Makes it a little bit easier to install. And set that right at the very end of the run of this elliptical shape that we're going to make. Set a screw in on the other side. Take your cable, run it all the way to the other screw that you just set, and wrap it nice and tight. The tighter that you make this cable, the better defined the shape.
So that cable that he's running is, as we saw in that previous video, is that length. That's going to be our 2A.
Shape of the ellipse is going to be. So you want to get it nice and tight so it works out really nice. Tie that off right there and pull it nice and tight. So you got really tight there. Now if you remember the definition of the focal point, or the way to find it, is that the focal point is half of our run, or half of our major axis. You take that dimension and you measure down from the very top to the top of the rise of this elliptical shape that we're going to be drawing, and measure down that distance. The easiest way to do it, you could do it with a tape measure. I mean, really, if you want to, measure across to our perpendicular. That's 20 inches. Measure down the 20 inches to where it intersects the major axis, and there's our focal point for this particular ellipse. It's a little bit difficult to do with a tape measure, so the easiest way really to do it is just take a little stick, a little story pole, mark it off, and I'll show you how to do that.
So this is actually a place where if he had a compass And if it was big enough, he could use a compass instead of what he's doing right here.
So that essentially is our 20 inches. Then raise it up, intersecting those 2 points, and wherever it intersects the baseline here, that's your focal point. We'll do the same thing on the other side. So now we've marked off the 2 focal points for this particular ellipse. Now remember, if we were to raise or lower the height of the ellipse, it's going to change where these focal points actually intersect our baseline. But for this particular shape, our ellipse, you can start here, come all the way to the top, and then come back down here. These are the 2 focal points that we need to make this shape. The simplest thing to do, unscrew the string. Now remember, don't change the length of this string. A lot of guys make the mistake, they think they have to change the length of the string. Don't do that. Take this screw and move it to this focal point. So now we're ready to draw the ellipse. This is the fun part. Doesn't get any easier than that.
I just want to go through real quick how he actually managed to realize or find the foci of that ellipse. So what he did is he started with the 2 endpoints here. So he knew how wide the ellipse needed to be, and he knew how high it needed to be. So he ended up, when he found these points right here, what he really did is he measured this distance off right here, and he measured it down to here. So if you go back and look at, if you back up the video a little bit if you missed it, so he measured this distance right here. So this distance right here, remember, was A. This distance right here is B. And then our foci is going to be right here. So this right here ended up also being A. So there's going to be a relationship here that we're going to talk about in a little bit in the next video, where they talk about this right here, the distance from the center to the foci being C. And what you'll notice here, I think, is that C squared plus B squared equals A squared. So it's a little bit different from what you're used to seeing the Pythagorean theorem labeled as, because you're used to seeing this as C. But that's how he actually found those foci, because this relationship exists.